recording. So, yeah, last week we were discussing about this traditional wastewater cleaning or traditional the common wastewater cleaning, and two of the nutrients, phosphate and phosphorus and nitrogen, occurring as phosphate ions, or maybe they don't occur as phosphate ions actually. Why wouldn't they? Yeah, it's because where is the pen now? Because if you have a, say, pH line and above something like 12, then we have phosphates.
You can't see what you're writing.
You can't see. Oh, shit. Thanks. Soon. Now we'll see. Another try. Phosphates. Now you see the line? Do you?
Yeah.
Yeah. So above approximately 12, the phosphate ion is the dominant species, but below 12, then it's the HPO4 2-. I would call this also phosphate. If I want to be very specific and speak exactly about this very ion, I would say hydrogen phosphate. That is the major species down to approximately 7, whereafter the dihydrogen phosphate ion is the major species, and below, say, 2 or something like that. Not H2O. No, I mean the business of element transformation. So it's phosphoric acid in that respect. But for any of these, it's common to speak about them as the phosphate system, the the 3 different phosphate ions, because formally it is only this one that is the phosphate, but I mean it's part of all the other molecules. Especially since natural waters, they have a pH slightly above 7, mostly, approximately 8 or 8.3 maybe. So then it's hydrogen phosphate that is the dominant species, but still there is a lot of phosphate in a water solution, even though it decreases to quite low levels, at least on a logarithmic scale. But still, since, for example, iron phosphate is very insoluble, one can precipitate compounds between especially iron 3 and phosphate 3-, whether this phosphate comes from hydrogen phosphate or even dihydrogen phosphate. The more distant you go, the more far away in the acidic region here, the more difficult it is to precipitate anything with iron ions. I don't think if you mix phosphoric acid plus iron 3 plus, then I hesitate to state that there will be a precipitate. Then they can probably coexist. They don't form any precipitate, but this has a reason, because the phosphate concentration here it's dominant, but here it decreases linearly, and here it decreases even faster. So the phosphate concentration in a region where we have pH 2 maximum, or maybe a little bit lower, the phosphate concentration is something like 10 to the minus 20 or so. And then a lot of iron is needed for actually precipitating anything. So from very acidus water, wastewater, for example, from industries producing acid wastewater and with some phosphate content, then you can't take care of the phosphate with iron or aluminum or anything else, actually. So the only thing then to do is to adjust the pH to up to reasonably close to neutral levels. Then the iron phosphates are possible to precipitate. And wastewater for taking care of nitrogen-containing species. The only species that we have been speaking about is ammonium ion and nitrate ion, but there are probably other type of ammonium compounds or nitrogen-containing compounds also that need, in principle, need to be taken care of. And the final product should be nitrogen gas, because then we can release it simply to the atmosphere. There are still problems to keep this eutrophication at low levels, so we don't feed the wastewater recipient with the nutritions. I showed these pictures last week, but these are slightly better. Freshwater production, 2 parts from the intake, and then adding some precipitation chemicals. Only in freshwater we add aluminum, and then this aluminum produces some flocks that we are allowed to sediment, and then it's essentially just filtered, maybe adding some chlorine containing compounds to kill bacteria, and then we have normal drinking water. They are slightly different, the freshwater production in Norsborg and the freshwater production at Lovön in the Stockholm area. They are slightly different, but otherwise there are only details that differ. And in principle, the same thing applies to wastewater cleaning. There are more steps taking care of the nitrogen containing compounds. It says here a bioreactor where one has bacteria that take care first oxidize ammonium to nitrate, and then reduces nitrate to nitrogen gas, or vice versa, reducing nitrate to ammonium and then oxidizing ammonium to nitrogen. I'm not sure exactly which type of process that is used. I think it's from nitrate to ammonia and then from ammonium to nitrogen gas, but I'm not sure. The extra thing with wastewater is that it contains a lot of more solid material from well, normal animal waste, so to say, from household, both in solution and then solid things also. These things could be collected in containers and producing, for example, methane or well, short, small organic molecules that you can use for heating and or running cars or something like that. Gases that are possible to burn. This is kind of fermentation, rearrangement of the atoms to some other molecules. It's not a lot of redox involved in this fermentation. It's just rearrangement. Well, you can never entirely avoid redox reactions, but it's not something like an oxidation or reduction or something like that. The idea is to get more or less pure water that one can with good conscience let out in the for Stockholm area in the Baltic, without any phosphates or without any nitrogen. And the only phosphorus is very, very low levels. It's only 1% left or something like that. But the nitrogen is less decrease, maybe 30% of the nitrogen coming in goes out here also in the waste, in the outlet. But I mean, that's still a decrease compared to just pouring it out without nitrogen cleaning. And this very nitrogen cleaning is actually probably the thing that is changing fastest in the wastewater cleaning industry, because new methods come and now and then it's on a 10-20 year scale. I think the bio reactor is a lot more advanced nowadays than it used to be, at least a little bit. But coming to well, close to zero levels in the outlet, I don't know if we ever will do, but Stockholm Vatten, both the freshwater and wastewater company in Stockholm, they take samples at a lot of different places. Here we have Riddarfjärden, for example. This is close to the border to the Salt Sea. And we should maybe try to take some sample water from approximately here. And then we should also try to take some sample from outside here. That should be possible, especially with our water fetcher, the bucket. Otherwise, these several different points, places are sampled, and water samples are taken and analyzed. And for example, the raw water intake at Norsborg freshwater plant, here's the temperature of that over a couple of years, and it seems that where is it? Yeah, it's a variation over the year. It seems that end of last millennia or up to 23 or something like that was a little bit colder during the summer. And on the other hand, the low temperatures during the winters, they were very low, close to zero. But obviously not a couple of years here in the beginning of 2000. I can't explain that, but it seems to be some kind of, this line here indicates overall increase in temperature of the water at the intake. It's not a lot, but well, we go from 7.3 to 9.8. That's 2.5 degrees. I'm not sure what this depends on, or that is to say, I don't have the slightest idea what it depends on. But it seems that the freshwater intake gets warmer. Nitrogen and phosphorus, measured in the quantity micrograms per liter. And here we have the beginning of the year, January to March, summer, and then the end of the year. At some decades from 1981 to 89, or from 1990 to 99, or 2000 to 2009. So one could have a look at the phosphate levels. At this place, it's more or less similar over the different part 3 decades. But what happens during the summer? Then it decreases quite much. At least the phosphorus, that is the soluble phosphorus. Decreasing phosphorus during summertime, and then in the autumn and winter, then it increases again. So how to explain decreasing phosphate levels during the summertime? We can look maybe at ammonium and nitrate also, or the total. Now we take ammonium and nitrate. Nitrate is high in the beginning of the year, but then decreases a little bit, quite much, 200 or something like that, coming down to 30, 40. This would be more easy to see if you made a plot of these values, and then the increasing again in November. Ammonium seems to be low levels here, and slightly higher and low levels. Why is it so much nitrate and so little ammonium in the water? This is well, maybe you don't know where this Lambarfjärden is, but it is somewhere. We can have a look at Lambarfjärden. It's up here. So it doesn't seem to be a particularly strange place. It's just a part of the lake here, sampling. And what is present apart from water and ammonium and nitrate in a lake? That makes the nitrate the dominant species in the nitrogen system. Think about the polar bear diagram. Maybe we have a polar bear diagram for nitrogen. No. Where is nitrogen? What nitrogen species are occurring in the polar bear diagram at different places? Ammonium is occurring where there is no oxygen.
And H3 is more to the left.
Yeah, and to the left, and in the upper part of the polar bear diagram. So nitrogen occurs as nitrate when there is oxygen present, and nitrogen occurs as ammonium when there is no oxygen. I don't know if one should try to interpret this slight increase here is in ammonium as a tendency of a smaller amount of oxygen. but it's colder here in the beginning of the year and the end of the year, so there will be more oxygen dissolved in the water. The solubility of oxygen increases with the decreasing temperature. So I think that is a general tendency. But just looking at the variation over the year, then in the summer it's low phosphates and low nitrogen. That seems to be the same. It's lower phosphates than the colder times, and it's lower nitrate, because that is the dominant form of nitrogen when, at least when the water is aerated. Because the summertime is a lot of vegetation, and the photosynthesis is running fast at high temperatures. I suppose so, at least. Dissolved oxygen has kind of important thing to do with the actual state of a lake. If we put out a lot of nutrients, then we increase principally the amount of planktons that are dependent on nutrients to grow. And this dead material that sets to the bottom consumes oxygen here, and especially if there is a stratification, that is a mix maybe of some surface layer, but then there is some cline. Some of you were discussing the halocline and thermocline, and depending on what parameter you measure, if you measure temperature, for example, then we can call this shift thermocline, or if we measure salinity, then it's a halocline. Halo for halogen, and sodium chloride, there we have chloride ions, which is the halogen ions, halogenide ions. In this state that we have a oxygen deficiency at the deep levels here, we can speak about anoxic states, and essentially without oxygen, organisms die. If it's only low oxygen, they may die, but I mean, definitely if there is a lot of dissolved oxygen that come from air or from photosynthesis, then it's a good state of the lake. But this is more or less also a natural process, that deep lakes and deep parts of the sea, they are usually not mixed very well, even though in deep sea, in ocean water, there is a lot of water streams that, for example, in the Atlantic, there is a stream from the south going down to the approximately at Iceland or something like that, sinking a lot of water, and it's when it cools down, it sinks, and then it makes a stream far down in the Atlantic, maybe to the bottom or something like that. There could very well be several different clines in a deep sea, like the Atlantic at least. And there is a lot of I can't explain because I don't know in detail the different streams that are occurring, but there are actually maps of that in oceanography, for example, of the streams in the big oceans. but that is not the subject of this course, I think. but there are possible ways that even deep sea can be aerated of a stream that from geometry of the sea floor, and that one could perhaps deduce that this should probably be some deep water streaming or something like that. But in a normal lake, it's very, very common with the stratification, and then it's hardly any mix. Only low oxygen levels. And the deposits, what happens with these deposits down here, and what happens with the sediments on the seafloor? Is it a possibility that iron 3+ could be reduced to iron 2+? Well, not necessarily, but I mean, if it's if you look in the pore bed diagram, where is iron 3+ stable, and where is iron 2+ stable? Well, then it's exactly same as for the nitrogen. The high oxidation state is stable close to in the vicinity of oxygen gas, and the low oxidation state, they are stable at far away from the oxygen gas area. So, for example, we were discussing this in the calculation exercises. If iron-free phosphate, if it is somehow reduced due to coming carbon down in some state, some kind of debris or a dead fish or something like that, or as stated in the Dagens Nyheter today, that the waste, the feces from the fishes are actually an excellent carbon sink, that they act as a possible carbon deposition at the bottom of the sea. But if we take up the fish, eat it, then we lose that carbon sink. On the other hand, a carbon sink will increase the reduction level or the reduced character of the seafloor. So maybe this carbon-mediated electron pump is more effective by a lot of fishes sending out a lot of feces. I never thought about that.
How does that reaction look like? The FeP, when FePO4 is reduced by oxygen, or I mean carbon.
Yeah. By carbon, let's see if we can make a I mean, carbon plus goes to carbon dioxide plus 4 electrons. This is an oxidation. If there is carbon or any type of carbon containing compound, carbon 0 goes to carbon 4, and then or even carbon monoxide, then it's carbon 2, but let's produce this one. Then we have an electron surplus, and then this, I mean, iron phosphate, that's very insoluble, but of course not totally insoluble. There are a slight amount of iron ions, very, very slight, but an iron 3+ plus an electron, that makes an iron 2+. And if there is electrons available, then we could expect, or I shouldn't say that we should expect, but there is a possibility for iron 3+ to be reduced to iron 2+. It's not necessarily so that iron 3 in a phosphate that is solid bound, but it has some equilibrium concentration for sure. It's not necessarily so that the electrons are first consumed there, but that is a possibility. If iron 2+ is produced, then of course iron 2+ and phosphate, they also 2+. They also, now let's see, this is more complicated than, because it's 2+ and 3-. So we take 2 of these and 3 of these. What does it make? It makes another iron containing mineral, or phosphate mineral. And this one, suppose this is the solubility, and here is another solubility. If this iron 2 phosphate is more soluble, then the effect of slowly transforming iron 3+ in the water by the presence of electrons is actually also increasing iron level in the iron level, and increasing iron, then it increases also the phosphate level in the water. One could perhaps set up and balance a formula with carbon, iron phosphate, and iron 3 phosphate, and iron 2 phosphate. I'm not sure that reliable thermodynamic data are available for these two compounds. There is some discussion in the literature whether they are, how insoluble they are, and also that relates then to say, for example, that delta G naught formation and such things. For the pure ions in water, then there are reliable thermodynamic data available, so then you can calculate a lot of things. The electrons, they are used for other stuff also. For example, sulfate plus how many? This is sulfur 6, so then we need 8 electrons to go to H2S or something like that. So if there is a lot of sulfate, and it is in the normal water, then there is a possibility that the electrons are used up. I'm not sure. This is a possible exam work to determine this equilibrium constant, maybe, but it's difficult actually, because they're quite small, both of them. But my guess is that this one is 10 times more soluble.
I have a question about the exam. Can I ask it?
Yeah, of course.
I thought about when you said about the calculations. Are we allowed to use the calculator during the exam?
Yeah, of course.
And the book of data as well, or?
Of course.
Okay.
But I don't think you. I can give you say thermodynamic data if you need that. So
Yeah, that would be very good.
yeah.
Okay.
And you will also get some Porbet diagram.
Yeah.
I haven't uploaded any old exam. I can do that so you can see how it looks like. So.
Hitesh did upload some more,
fine,
but you
fine.
can upload some more if you want to.
No. They are all quite similar. So.
Okay.
Yeah.
Okay. Thanks.
So time runs 9:54. We should have a coffee break or something like that. Is it 15 minutes? Is that okay?
Sure.
Then we take to 10 past.